This is problem 3-73.M. It's on page 168. Figure P373 shows an aluminum cylinder being capped by two end plates that are held in position with four steel tie rods. A clamping force is created by tightening the nuts on the ends of the tie rods. Compute the stress in the cylinder and the tie rods if the nuts are turned one full turn from the hand-tight condition. Okay, well, let me ask you some intuitive questions that you should be able to answer. The rods, basically the bolts, are those rods in tension or compression? They're in tension, right? So the cylinder is in compression. Okay, good. Now, it seems a little confusing. There's something to do with this tightening bit, right? If we tighten the nut one full turn, that means the nut's going to move down on the bolt by one thread. So one question we would have is, what's the distance between adjacent threads on a nut or a bolt like this? Well, what does the specification say? What kind of bolt is this?
Metric.
It's a metric. What's the designation? M10 by 1.25 thread. You guys know what that means? Well, the 1.25 thread means that the spacing between adjacent threads on the bolts is 1.25 millimeters. That's all it means. English bolts are the opposite. Basically, in English bolts, you designate them by how many threads per 1 inch of length there is. But metric bolts, they just give you the pitch, the distance between two adjacent threads. So if we tighten the nut down by one whole turn, then what's the change in the position of the nut on that rod? How much distance does it move? 1.25 millimeters, okay? So that's what it means. Now, we're supposed to find the stress in the cylinder, and of course, you'll need to reference the book if you're watching the video, because you'll really need to look at this figure. But we need to know the final stress in the cylinder, which we expect to be a compressive stress. One thing to note, though, is that the force in the rods, and I'm going to deal with the rods all as one group. Does that make sense? So all four of them are doing the same thing. I'm just going to, as far as the stress and force analysis goes, I'm just going to combine them all together. Okay, there's no point in treating them separately. At least I don't think I end up doing that at all throughout this problem. There's no need. But do you realize that the force in the rods must be equal to the force in the cylinder? Otherwise the top would move, right? Because it has to be balanced. So that you can consider that plate on the top as a free body. The force from the bolts pulling down on it must equal the force from the cylinder pushing up on it. So that's something that we can use. But what else? Well, we have to be a little careful, because that deflection that I talked about, that deflection is not the deflection of the rods by themselves or the cylinder by itself, right? That's a relative motion of the nut on the thread. I mean, think about it. Both the cylinder or the tube, whatever you want to call it, is just going to, and the rods, are just going to act like two springs, right? Basically, if we make a reference point on each of these at the same height initially, well, as we tighten down the nut, all that's going to happen is the cylinder is going to deform like this, and the rods are going to deform like this. Does that make sense? So that delta of 1.25 millimeters is not this, and it's not this. But it is the difference between the two. Does that make sense? Or it's the addition of the two. If we take these as an absolute value, you could say that the deflection, kind of making better, small Greek delta, of the rods plus the deflection, of course both these being in an absolute sense, of the cylinder is equal to the pitch of the thread. Does that make sense? So in other words, the deflection of the rod plus the deflection of the cylinder is going to be 1.25 millimeters. Okay, that's all this says. Okay, because the rods are going to move up a little bit, the cylinder is going to move down a little bit. And I added this bit just to hopefully help with your intuition. That's the section of the rod sticking up above the nut. As you can see how these things move. But we should be able to write the deflection of the rod and the cylinder with the equations that we've had before. In fact, let's see in the slides, slide number 4, the deflection can be written in terms of force, length, elastic modulus, and area. So why don't we do that? So let's write the deflection of the rod. Well, that's just the force in the rod multiplied by the length of the rod divided by the area of the rod and divided by the elastic modulus of the rod. Now, what I'm going to do here is I'm going to deal with all of the force in all the bolts together as if it's one. And so this area will be the cross-sectional area of 4 of them. Does that make sense? So if I need to, I'll calculate the cross-sectional area of one rod, multiply that by 4, because I'll just assume that all 4 of the rods are carrying the load equally. Okay? So this is the deflection of all. It's not like it's 4 times the deflection of one rod, right? They all deflect the same amount. So there's a slight subtlety in going from here to here. But the cylinder is a little more straightforward. The force in the cylinder multiplied by the initial length of the cylinder divided by the area of the cylinder and the elastic modulus of the cylinder. Well, that's just straightforward because it's just one member. Anyway, all of this is equal to the total deflection of 1 1/4 millimeters. Now, to calculate the area of the rod, I went off to the side and did that, so I'll do the same over here. I'll just jot it down. The area of the rod, like I said, I've got to calculate all the area, all the cross-sectional area that all of the rods contribute. So that's going to be 4 times pi times the diameter of the rod. I'll just plug it in. The rods are 5 millimeters in diameter, in radius squared. Let me make sure I did that right. Yeah, because each of the rods are 10 millimeter rods. So this is just a pi r squared, but we've got 4 of them. And so that comes out, I better write it here. That comes out to a total area for the rods of about 314.16 square millimeters. Okay, so that's how much area all of the rods contribute to this, and that's what's going to go in right here. And then the area of the cylinder, well, the cylinder, if you look at the figure, it says that it's an aluminum tube actually, so it's hollow, it's not a solid cylinder, and it's 150 millimeter OD, 138 millimeter ID. And so what I did to calculate that, you know what, I think I'm going to need calculator help because I bet I made a mistake here. I used the diameters instead of the radii to calculate area. Yep, so I'm going to need your help. Let me show you what I did. I went pi 150 squared less 138 squared, and I called that the area, but that's not right, is it? Because it has to be pi d squared over 4, right? So I need an over 4 here. So calculate this if you would. Of course, it'll be in millimeters squared, and I'll have to update my solution. Okay. So once you've got a number, just let me know what it is. You should get something around, let's see if I divided that by 4. You should get something around 2,500, a little more.
So 4398.2.
4398.
That's what I got.
I got that too.
You mean I made 2 mistakes? Because I got 10,857, so I expected to divide that by 4. I guess I made a calculator mistake too. Well, what do you know? How much was it?
4398.2.
398. Let's drop the point to 2. Well, we'll keep it. We kept it here. Millimeter squared. Okay, so either you guys made a mistake or I made a mistake. I'm betting I did. So I was pretty tired when I was working on this. Anyway, so there's the area that the cylinder contributes and the area that all the rods together contribute. Let me jot it down over here so I can use that space. So the rod area is 314.16 square millimeters. The cylinder area is 4398.2 square millimeters. Okay, thank you guys. All right. Now, the length of the rods and the length of the cylinders, at least the part that's stretched, is the same initially. So do you see how the product here and the product here are exactly the same and could be factored out? Okay, does that make sense? So all I did was I said, well, this is just FL, I'll call it that, rather than writing the subscripts all the time since it's the same thing, times 1 over area rod, elastic modulus of rod, plus 1 over area of cylinder, elastic modulus of cylinder, and that's equal to the deflection, the 1 1/4 millimeter deflection still. And what I did is I decided to just solve for the force that's applied to the 2, and so that's easy. That's just P over L, divide through by the L, and then divide through by this larger factor, 1 over area rod, elastic modulus of rod, plus 1 over area of cylinder, elastic modulus of cylinder, and that's it. So now we should be able to calculate the force that's applied to all 4 rods together as a whole, or the force applied to the cylinder or the tube, whatever you want to call it. Okay? All right, so let's plug in the numbers. The force is 1.25 millimeters divided by the length. Well, the original length of the system was 450 millimeters. I hope I copied that down. Yeah, 450 millimeters. And then the rods were steel. Where did it say that? Yeah, 4 steel tie rods. And so the area of the rods total was 314.16 millimeters squared. And the elastic modulus of the rod, well, it's steel, so what is it again? You have it memorized now, right? 207, right. So 207 gigapascals. Now when you multiply millimeters squared by gigapascals, what do you get back? You get back force. How much force do you get? It's kilonewtons. And another thing you need to commit to memory is a kilonewton per millimeter squared is a gigapascal. And it's going to be really handy in working all the problems in this class. Okay, so anyway, that takes care of this first bit. The next bit, help me out. What should I write for the area of the cylinder? What I've got over here, right? 4,398.2. How about for the elastic modulus of the aluminum? I'll wait for you on this one. Where would you find it? Back of the book, right? When someone has a page number for me, just fill it out. There is a table in the back of your book that is dealing completely with aluminum alloys. If you don't have the material section of your appendix bookmarked yet, you should do that now. Page 718, thank you. You'll notice it's a footnote at the bottom of the table. It'll tell you the elastic modulus of aluminum. Do you see it there? 69 gigapascals. Good job. Okay? So there's the elastic modulus. So we're going to end up with, let's see, the millimeters go away. We'll end up with kilonewtons of force, right? Because the millimeter squared times gigapascal will give us kilonewtons, which is in the denominator of the denominator, so it will end up in the numerator. So plug this long equation, if you will, into your calculator, and you'll get something different than what I got. I used the wrong area. I do recommend you bring your book and your calculator to class. One of the reasons that I have you plug numbers in calculator or plug numbers into your calculator like this is so that you get used to doing it, because you'll have to do things like this on exams anyway. So I think it's good practice to make sure you get familiar with your calculator and can do the problems like we have in this class. Work them.
I got 148.76.
148.76. Anyone second that? Okay, we've got a second vote. Good. I got 166 kilonewtons, but of course mine is wrong. 148 kilonewtons, 149 or so is fine.
I think the area of the cylinder is wrong, because I think everybody thought you wrote down 130 instead of 138.
Ah, I did write
Yeah.
138. It was not
So
130.
the answer, I mean, the actual area was 2,714.
That's what I expected. It was more
Yeah.
like that.
Yeah,
2,714.
yeah, because I calculated like, I did 132, and that's where everybody else got like 140.
See, well, a lot of times we don't mess with the small
Yeah.
stuff. We usually make bigger mistakes than that anyways, so why bother? Okay, that sounds more like what I expected, because I didn't think I was that far off in my answer, as far as my method goes. 2,714. Okay, thank you. So let's try this again. Thank you for catching that.
134 kilonewtons.
134 kilonewtons. Anyone second that? Sure? I didn't see. Yes? Okay. All right. So 134 kilonewtons. All right. Now, that's the force in the rods as a whole and in the tube or the cylinder as a whole. So now we can calculate the stress in the cylinder very easily. All we have to do is take force or area. Now that we've got the right cylinder area, that's 134 kilonewtons per an area of 2,714 millimeters squared. So if we have kilonewtons per millimeter squared, we'll get gigapascals. Good. So plug it in your calculator. I'll write out the equation for the rods as well. Okay. Anyone have results?
For the top one, I have 0.049.
What, 0.49? So wouldn't that be 49 megapascals?
Yeah.
0.49. Okay. So there's the stress in the cylinder. Anyone have the rods or second the cylinder? Second cylinder, good.
0.43.
0.43 in the rods, so that would be 430 megapascals in the rods. Anyone agree with that? Okay. All right, so the rods are taking, or the rods have more stress in them basically than the cylinder. That's not really a big surprise since the rods have less area than the cylinder does. But of course, the cylinder is softer than the rods. So. Questions, comments? All right.